I'm gonna try something new today. I'm going to probably not eat my salad while I'm teaching, but also I'm trying to see if I can record using Facebook Live as a video recording option. That way we can have like a video cast, possibly. I'm going to see if it works. If it doesn't work, then I'll just convert the video to audio, and then I'll upload the audio normally, the way it normally is, and then I'll see if there's another way I can do it. I don't know, I just feel like the video podcast is like better. I don't know, like it's easier to follow along. You can like watch it at different speeds, so you're like watching and listening at like times 2 or times 1.5 speed, whatever it was that you wanted. I don't know. I'm trying to make stuff happen. So, all right. So we have a few announcements. We will be finishing midterm 2 material on Wednesday. Your midterm is not until 2 weeks from this Thursday. So not next week, the week after. Meaning we're going to be ahead of schedule, but that's okay because midterm 2 doesn't have that much material on it anyway. And also because like the last section of the quarter is a little bit heavier. It's not super bad, but it's like, what is that, like 4 weeks worth of material? So the reason I'm bringing this up is because I like to do my midterm review session or whatever, where I do my own midterm. So I wanted to ask y'all, ignore this. Okay, so I'm going to make a calendar. You don't need to write this down. Tuesday, Wednesday, Thursday, Friday. We are here. Okay. Shaded areas are content review. I believe this is the 24th. Don't know. So if we were to choose from the starred areas where we would like a content review, where we would like a midterm review, would y'all like it to be held, like, in which box? If we hold it here, that will be as soon as we finish the material. The material might be more fresh in your minds, but I would think y'all would want it somewhere more over here to give you more time to review. I don't know how much y'all like this the day before your midterm, so I think that it'll be strongly between these two. Does anyone prefer these over the second week? Okay, so we can just rule those out, right? Okay, so between this one and this one, like show of hands, who prefers Monday? Okay, other show of your other hand. Who prefers Wednesday? Okay, so Monday strongly won. All right, so we'll do it Monday. So that means that this, and this will be final material. I'm not gonna like not use those days. I'm gonna have to use those days. So here, and then here, I will be doing reviewing material for the final. 2 weeks from now will be the midterm review date. If y'all want to change this at any point, you can let me know because I can literally change it like 5 minutes before lecture. If it's Monday and y'all feel like we're not ready for a review yet, I can postpone the review till Wednesday, which means I'm flexible with your schedules. Okay, that being said, what would that be? The 23rd? 22nd, 21st. Yes, 21st. All right. Any questions? Okay, more announcements. I don't know if y'all do the practice problems that I post. I posted one today for the material for today's lecture. Those practice problems, I think, in my estimation, are pretty hard. If you can do those practice problems, you will be able to do any of the diazonium benzene salts, whatever they're called, problems on a midterm. If y'all can get those done, that's content review 9 practice. Any diazonium salt benzene problems on a midterm you should be able to do, so just heads up. They're all synthesis problems. Those problems don't cover everything we're going to do today because I forgot that we were doing other stuff today as well, so I'll write up more practice problems for like the second half of today's lecture. Okay. That's the last announcement. Any questions? I talked a lot. I'm tired. Okay. So, what did we do last time? I'm blanking out really. We started talking about, okay, so we did reactions of amines. I'm gonna have to look. We did reactions of amines, and yes, I'm gonna review them because I rushed through it at the very end. So, we did reactions of amines, and we had three. That's all we did last week. Last Wednesday. We did three reactions. The first one was the exhaustive methylation or the Hoffman elimination, where you are removing the amino group from the carbon chain and performing an elimination reaction by continuously adding methyls to your amino group, to your nitrogen. This is the concept of the exhaustive methylation. This was the exhaustive methylation example, I believe that we did. Did we do another one? No. So this is the one that we did, where we talked about, okay, so I have an amine, and then I stick some nitrogen, some methyls on it to the nitrogen, and then I'm going to have to break a bond somewhere because this is a positively charged nitrogen, doesn't want to be positively charged. It's going to break a bond. Which bond is it going to break? It's going to break the bond of the carbon that will give it the least substituted alkene, because this is a Hoffman elimination. If you remember from 118b, Hoffman elimination refers to the least substituted alkene. So, and then if we have more methyl groups to attach in our solution, we can continue to methylate the amino group, and eventually it'll pop off and give us a alkene of some sort. So, we did this, and then we did the manic reaction, which is sticking two carbonyl compounds together, a less reactive and a more reactive. And we said the easy way to look at that were these three steps right here. So I gave this as an example, and we said, okay, we know we always have a less reactive, a more reactive, and more reactive carbonyl groups and amine. So what we're going to do is we're going to replace the oxygen of the more reactive carbonyl group, replace the oxygen with the amine, and then remove the double bond here. This isn't the mechanism again. This is just an easy way to solve the problem. And then we attach the alpha carbon of the more reactive carbonyl group, so the alpha carbon, one carbon away, to this carbon right here that was originally part of the carbonyl. And that gives you the manic product, I guess. I don't know what to call it. This is a manic base. So there was that reaction, and then lastly, the one that I rushed through and could be the most important one was the nitrization reactions, where we are adding a nitro group to the amines. That means that we are going to be adding NO2 to whatever amine it is. If it's a primary, it gives us a diazonium salt. If it's a secondary, it gives us this thing. If it's a tertiary, it's not really useful for anything. We don't really care about that one. We can do nucleophilic substitution, and we can do elimination reactions with diazonium salts. And then we showed a mechanism for it on the back end. And then we talked about, so this is the mechanism for it, where I'm converting the amine is getting converted into a diazonium salt, which will be intermediate for things that we're about to show today. A bunch of stuff we can do with diazonium salts. This is specifically diazonium benzenes, or whatever the name for it is. But we also did talk about this side reaction here, where we can turn a carboxylic acid into a methyl ester. I briefly went over that, and I forgot to include the mechanism for creating the diazomethanes, which is this compound. I forgot to show the mechanism for that, so we're going to start off with that today. Any questions? Okay. All right. So let's talk about that side note reaction. Side note reaction. So for the side note reaction, again, it was the conversion of a carboxylic acid to a methyl ester using a sort of diazonium salt known as diazomethane. But how do we make this? Oh boy, that's not clear, is it? Okay. So how do we make this thing? So first what we're going to need to do is we're going to need to start with an amide. Start with an amide that has two methyl groups on it. Excuse me, one methyl group on it. So we start with this amide, and what we're going to do is we're going to perform the nitrization reaction with this amide. So when we're doing the nitrization reaction with the amide, we treat the nitrogen on the amide as an amine. And so what do we remember? So first of all, this is a primary, secondary, tertiary amine. It's a secondary amine. If we do the nitrization reaction to a secondary amine, what do we get? I don't know the name for it. But what happens? We attach the nitro group to the amine. It just sticks on. It doesn't turn into a diazonium salt. It just sticks on. So now, this nitrogen, and this methyl group, we're going to react it with a base at cold temperatures. We don't need to know the mechanism for this, just understand where it comes from. React it with a base at cold temperatures. This is what is going to give us our diazonium salt. Excuse me, our diazomethane. So when we react it with a base, probably forms a carboxylate and kicks that thing off, and it might turn into water. But so this reaction is what gives us the diazomethane. That's all extra that I wanted to say about the side reactions. So today we're going to be talking about the benzene diazonium salts. We're going to be talking about that today. Today we're going to transition into all of the benzene type reactions. So in order to do that, what we're going to do is briefly go over the reactions of benzenes that we did in 118B. We're going to make another tree thing, and we're just going to review those reactions really quickly. So, reactions of benzenes. So first we're going to talk about the reactions of the benzenes, and later on today we're going to be talking about diazonium salt benzenes, and then we're going to talk about the benzylic carbon. We'll talk about what that means later on. Is that today? Yes, it is. So the benzylic carbon, and then we're going to talk about phenols, which is a benzene alcohol. It's a benzene alcohol. These general reactions apply to all of those benzenes. So we can perform these general reactions on all of those benzenes. That's why we're going over them first right now, in order to get an idea of what we can use ahead, for what we have ahead. So let's create our tree. Okay, nice. And we have 1, 2, 3, 4, 5 different reactions that we learned in 118B. So 1, 2, 3, 4, 5. The first reaction was halogenating, and in order to do that, we needed the halogen in diatom form. That can be Cl, Br, and then its respective catalyst. We then did nitration, so adding an NO2 on it. And in order to do that, we needed HNO3 and H2SO4, non-nucleophilic acid. And then that would nitrate. I don't know the word. Our benzene, it would add a nitro group on it. And then we said we could convert this nitro group into an amine by doing a certain reaction. So we can convert to NH2 using this reaction right here. That'll convert it into an NH2 for us, and then we can convert the NH2 back to the nitro. So we can do the NH2 back to the nitro using MCPBA with MCPBA. Sure, I'll include the third one. And then we can also convert.
It's frozen.
Is it? Nice. So we can do it with this, or we can do it with so we can use either one of those two to reduce the nitro group to the amine. This one only does it to the amine, only to the nitrogen. If y'all remember, this will only reduce the nitrogen group, the nitro group to the amine. This one will reduce the nitro group to amines, and it will also it'll get rid of any carbonyls. So if I have a carbonyl attached to my benzene and I react it with this, it'll remove the double bond O, and then it'll be a straight chain carbon. So this is review. I'll write that on the top, actually. Review. So we then said, I'm going to make this arrow a little shorter. There was another reaction that we could do. We could sulfonate our benzene, and this was through using H2SO4, and this was the only reversible benzene reaction that we had. So this reaction was reversible. I could add this group and then take it off, and then that's useful for some synthesis things. We could also alkylate our benzene using a haloalkane and its respective catalyst. But we had some issues with this, if y'all remember. We had the issue of carbocation rearrangement. And we also had the issue of poly addition or polyalkylation, meaning that I could add multiple carbon chain, multiple R groups to my benzene. And in order to combat that, we developed another method of attaching carbon chains, and that was the acylation method. So Friedel-Crafts alkylation and acylation. where we either use an anhydride or an alkanoyl acyl halide. Either one we can use to attach an acyl group or a carbonyl carbon chain to our benzene. And then this helped with the issue of carbocation rearrangement because we never formed a carbocation. And it helped with the issue of polyaddition because we can't have more fetal Crafts acylation or alkylation, if you remember. If we have a meta-directing group attached to our benzene, that is a meta-directing group. So once we do the reaction once, we can't do it any more times. And we can remove, again, I'm going to repeat this, we can remove the double bond O with this reaction right here. This reaction will remove the double bond O. Those were the five reactions that we did with benzenes in 118B. And again, all of these reactions are applicable to everything we're going to do here. So know them. You don't need to know mechanisms or anything. Just know that if I use this, especially this one, like super important. If I do this, I'm attaching a nitro group. If I'm doing this, I'm attaching a sulfur group. If I'm doing one of these, I'm Friedel-Crafts alkylating acylating. Just know those. And any questions about this? Because if not, then we're just going to jump straight into the reactions of, creating the benzene diazonium salt, and then we're going to do all the reactions of it and everything. So, without further ado, okay, wait, should I keep this up here for another minute? I'll probably fit it on the bottom. So, synthesis of benzene diazonium salts. We already did this. This was the last thing that we did on, what was that day? Wednesday. And it was simply taking a benzenamine and performing the nitrization reaction on it. So that's NaNO2. I have to use an acid. I can use HCl or H2SO4. Either one works. If I am at 0 degrees Celsius. If I'm at 0 degrees Celsius, this won't act as a nucleophile. This one can act independent of temperature in forming the diazomethane. In forming the benzene diazonium salt. This will give me benzene diazonium salt. We did this last week. And that's pretty much the only way to synthesize it is you're going to need an amino group, you're going to need an NH2, and you're going to need to perform this reaction. Yes?
Does the positive charge stay on the nitrogen, the benzylic nitrogen?
Say it again, sorry.
Does the positive charge stay on the benzylic nitrogen, or is it the resonance going back and forth?
It resonates going back and forth, but it's more stable on the benzylic nitrogen because we're going to talk about that later on today. Benzylic atoms are more stable, whether they be positive, negative charges, or radicals. So it's the main form is on the benzylic nitrogen, but not too important. Maybe unless you're doing a mechanism. So, good question. Any other questions? Okay. So now, let's talk about reactions. In my notes, all of these reactions didn't have mechanisms, so I'm assuming that you won't have to know the mechanisms for them. But just like the normal benzene reactions, these reactions are reactions that you need to be able to recognize. If I see it on a major product problem, oh, I know what that's doing. Or if I need it in the synthesis question, I need to be able to recall certain reactions. I don't know why I can't speak today. So, reactions of benzene diazonium salts. Make it another tree. This time we have 6. 6 different reactions. So, the first reaction is halogenation and I guess nitrylation. So, attaching a halogen or a nitrile group, a CN group, using where X is equal or can be, it can be a Cl, it can be a Br, it can be an I. We now have a way to add iodines to our benzene ring. And we can also add a nitrile. We can add a nitrile using this. So it would be CuCN or CuI or CuBr or CuCl. To add iodine to it, you can also use use Ki. This is another method of addition of the iodine. So you can use CuI, you can use Ki. Any one of these work. And what I want you guys to notice is that here it's not necessarily an addition to the benzene ring. All of these reactions, most of them, are a replacement of the N2. Before, when I would add bromine in a certain way, that would add it to the other spots, other carbons on the benzene ring. This is a replacement of what I started with, the N2 positive charge, the diazonium salt. That's what I'm doing here. I'm not adding, I'm replacing, I'm substituting. I can add a fluorine using a different reaction, NaBF4. So I can add all of the halogens to a benzene ring using a diazonium salt. I can add a nitrile to a benzene ring using a diazonium salt. And these reactions are replacement substitutions, not strictly by the definition of the word addition. They're not additions to the benzene ring. All right. I can turn my benzene diazonium salt into a phenol. I can turn it into a phenol, into an alcohol, by using acid and water. Acid and heat. So this acid is nucleophilic. It has more nucleophilic properties than, say, an H2SO4. So it'll act as a nucleophile and will attack that carbon and replace the N2 with an OH. Okay. I can add other benzene rings. To my diazonium salt. What this will do is the benzene ring will act as a nucleophile to my diazonium salt, to my N2. Meaning, so let's think about this. A benzene ring, what does it have a lot of? It has a lot of electrons, because it has a lot of electrons. They're just there, right? Have a positive charge on my nitrogen here, right? On the nitrogens. So, if there's a positive charge on the nitrogens and the benzene ring has its electrons, what I can do is I can link the benzene rings through, I'm going to call it the diazonium bridge. That's the name I made up. I can link them together through there. This originally had a positive charge on it. This had electrons, so it'll reach its hand out, say, here, take my electrons. They form a bond, and then I have the coupling here. This can be written differently. Can be written like this as well. So don't get confused. So next, the hardest, or what I believe to be the hardest reaction of these reactions, is adding a benzene that has an activating group on it. Adding a benzene that has an activating group on it. So here I was adding a benzene with nothing on it. Now I'm adding a benzene with an activating group on it. That can be an amine. That can be an OH. That can be a methyl group, so on and so forth. So what do we know about activating groups in general? Activating groups, where do they direct? Ortho-para. They direct ortho-para. If I'm adding this diazonium benzene to the benzene with the activating group, where will this benzene add? It will add ortho or para. It'll probably add para because this thing is huge. So, this is another form of benzene coupling, but now with regiospecificity. We are concerned with which carbon we're attaching it to because of this activating group. So, act means activating group. And remember that the activating group is ortho-para directing. So it'll add para. It's cool with everyone? This is probably the most difficult reaction out of these. Because this might look easy, but we're going to go over an example later on where we might get confused, might not. So, last reaction is just removing the diazonium part of my diazonium salt. Just removing it. And I use phosphoric acid, H3PO4. And then it pops off. Replaces it with a hydrogen. Replaces the N2 with a hydrogen. I get a clean benzene back. These are all of the reactions that are specific to diazonium benzene salts. Benzene diazonium salts, whatever you want to call them. We're not going to go over any mechanisms because they weren't in my notes. I don't know if they're in your notes. Questions about this? We're going to go over a few examples using them, seeing like how to use them in a question that could be posed to us. Before we do that, let's talk about these three specifically. Say, notice these reactions don't add to the benzene. They replace the N2 plus group. The reason I'm emphasizing this is because there's a possibility that I got this wrong on a midterm or final, and I felt really stupid. There's a possibility that I felt very stupid about it. So don't get confused, please. Yes.
Is a electron withdrawing group, is the benzene going to be strong enough for it to react to the
Talk about this one.
diazonium?
Talk about
Yeah.
Yeah. I feel like you'd get no reaction because this is positively charged. This group is positively charged, and the electron withdrawing group would cause another carbocation to form on the ring.
Right.
So you'd have a positively charged. You wouldn't have any like electron source to do an electron donation reaction or an acid-base reaction, essentially.
Right.
Yeah. So the key here is that because this is an activating group, it can push electrons into the ring, and then there can be part of the ring, specifically the para part, that will be a carboanion that will help facilitate this reaction. Good question. I don't know if I put it up on the drive, but I think I put up the resonance of electron withdrawing groups and electron donating groups of benzenes on the drive. I don't know for certain if I did, but I have some recollection of that. I will check after class, and if I don't have it, I'll post it there. For those who are curious and want to see how the benzene resonates when you have an electron withdrawing or donating group, or if a group is an ortho, para, or meta, how that differs, I'll do that. So, are we cool with this? Cool with these reactions? These reactions and the reactions that we just reviewed before. Let's go over some examples. Let's go over, some examples. So, example number 1. If I want to go from this benzene to this benzene, if I want to stick 2 bromines onto the benzene, how can I do that? At first, you might think like, oh, okay, I have a reaction for brominating a benzene. That's Br2, and its catalyst FeBr3. I can just do that, and then I'll be fine. The problem with that is, so you do it once, and then you get 1 bromine stuck to it. Bromine, is it orthopara or metadirecting? It's orthopara. So the next bromine will stick either ortho or para. It won't stick in the meta position. These bromines are meta to each other. That's a problem. So we want to find a way to make bromines meta to each other. How can we do that? We can do that by using our diazonium salt. So let's do this. The first step I'm going to do is sticking on the nitro to my benzene. Which will give me the nitro group, and then I want to eventually convert it into a diazonium salt, we said. That's where we want to get, and then we'll play with it there and see what it does. So in order to get to a diazonium salt, I'm going to need to make an amine. I can make this into an amine by doing this reaction, which gives me So, I'm here. What do I notice about this? What can this do? Or where did this add? What kind of directing group is it? This is orthopara. This is orthopara. This is a meta-directing group. This would be an orthopara group. Yeah. So if I decide to brominate here, I can brominate orthopara, and then I'd have two bromines that are one carbon away from each other, which is what I have in the answer. Or if it decides to get funny on me, I can brominate ortho, and I would still have two bromines that are one carbon away from each other. The key here is that this is a stronger activating group or a stronger directing group than the bromines. So this will tell me where my things are going to go. This will tell me that my things are going to go orthopara to the amino group, not to the bromines. And what's cool about this is that once I stick this on, I have a way to take it off. We talked about it earlier on the top of the page. There's a way to take this thing off. So if I can stick on my bromines that are one carbon away from each other, and then remove this group, I got my product. Does everyone understand that? Does that confuse anyone? Okay. So that's what I'm going to do. And the reason I don't convert this into a diazonium salt first is because, as far as I know, I don't know if the diazonium salt, where it falls on the spectrum, it's probably closer to being a deactivating group, so like a meta-directing group, but I don't know that for certain. Actually, it doesn't participate with the resonance of the benzene at all. So I don't know if it affects the addition of anything. I don't think it will. So the N2 doesn't dictate where anything goes to the benzene, so I can't react anything with an N2 on a benzene and expect that N2 to dictate where other things go. So the amino group does do that. Long story short, remember we said that NH2 is an orthopara directing group, and here I have both the ortho and the para positions open, so I'm probably going to get double bromination of the ortho position and bromination of the ortho and the para position. Right, yes?
Can we block it with sulfidation?
You could, but that would be an extra step that doesn't serve a purpose, and we're about to show why. So, now I want to get rid of this group. Do y'all see how, I'm going to try this. If I were to cut, that doesn't help. If I were to cover these, actually I can use my fingers. If I were to cover these, that's my product, right?
Yeah.
That's my product. I don't need to block the para position with the sulfur because all I need to do is remove the nitrogen and then I get my product. You can do it with the sulfur, that's just an extra step for you. So, in order to remove this, what do I got to do? Turn it into a diazonium salt. Very good. This will turn, so that's the reaction for turning amines into diazonium salts. And how do I remove the diazonium salt from the benzene ring? H3PO4. That's on the top of the page. We just discussed it a few minutes ago. A powerful reaction because we can do a lot of stuff with it. Yes, you could have blocked the para position again, But if we did that, we would have had to do a reaction to block the pair position and then do a reaction to remove the sulfonated group or the sulfur group from that pair position. So that's two extra reactions that we need to do. And that's not cool. Did you have a question about that?
Would H3PO4 serve as the acid and remove that? I mean, it really doesn't matter. Just don't get it.
I assume wouldn't matter. There are cases where other reactions where the type of acid you do use matters. I assume this one doesn't matter because it's non-nucleophilic. So yeah, as long as you heat it. But the point is that would be an extra step that we wouldn't need to do.
Yeah.
Yeah. Yeah. Yeah. So, does this make sense to everyone? This is clear. This is cool. Calm and collected. All right. We got a few more examples that we're going to do. Two more. The first one is again, or the second one here. So this would be example number 2. So here, I'm starting with an already brominated benzene, and I'm trying to get to this group. Trying to get here. How can I do that? How can I add iodines? How can I add iodines to a benzene? Do we know a reaction for that? What do I need to do? I need to somehow get a diazonium salt on my benzene. And then I need to turn that into the iodine. If I were to try to add a diazonium salt here, what position would it get stuck on?
Orthopara.
Orthopara. This is meta again. It's one carbon away, or there's a carbon in between. So if I were to try to stick the NO2 and then convert that into an NH2 and then convert that into an N2 and then convert that into the I, I'd be adding it ortho-para. I wouldn't be adding it meta to the bromine. This is a case where what we need to do is remove the bromine and then start with a fresh benzene and then essentially start all over. This is a reaction, it was in my notes. We haven't really discussed it, so I'm just going to walk you through it and show it anyway. If you turn this benzene into a Grignard's reagent, you can remove this Grignard's reagent by doing an acid workup. You can remove the Grignard's reagent by performing an acid workup. We didn't really talk about this at any point, so that's why I wanted to show it to you. This might be useful. We can remove the Grignard's reagent by performing an acid workup. And so now I have the ability to do whatever I want because it's a fresh, clean benzene. So what am I going to do? Well, again, I need to make my bromine and my iodine meta from each other. So I'm going to add a meta-directing group onto my benzene. And a handy one that I can use because we're going to need it later would be NO2, meta-directing group. And since it's meta-directing, that means I can add the bromine meta to the NO2. And so all I need to do now is convert that NO2 back or convert it into the iodine. So I can do this. So again, this is the typical, we're going to do this a lot, reaction of converting NO2 into diazonium salt, which would be to make the NO2 into an NH2 and then into the diazonium compound. So SN2 over HCl will do that for you. It'll do that for you and then get you to this phase. I feel like I'm running out of room, so I'm going to cross over to the middle here. And then to convert the amine into a diazonium salt, do the nitrization reaction. This one doesn't need to be 0 degrees, I'm sorry. This one does, though. Okay, finally. We can turn it into, we can replace the N2 with the iodine. We can do that using CuI, Ki, either or, gets the job done. The tricky part of the synthesis was just doing this, knowing this, figuring out how can I remove the bromine from the benzene and start with a fresh, clean slate. There's probably other mechanisms, or you can probably like work your way around not removing it. I didn't put any thought to that, so I'm unsure. Yes.
Why are we not able to use iodine Lewis acid catalyst?
I believe that iodine has the. I believe iodine has the lowest nucleophilicity. So, and benzenes are aromatics. We discussed this in one TV. They're not very reactive. So it's very difficult to do it that way. You'd probably need a lot of heat, and that's just not something we want to do. This reaction, we can actually do it we need to do it at freezing temperatures, right? So this reaction is a better way to do the synthesis. I believe that is a thing. It's just not a very common practice because of the difficulties around, the reaction itself. All right, we got one more example, which we are going to talk about the coupling that we discussed earlier, the attaching a benzene ring to another benzene ring, essentially. So, the example. Say I want to make this compound. Say I want to make this compound. Y'all might have seen something similar to this in lecture. I think I changed it up. I changed it up for my notes, but I don't know how it is in yours. So say I want to make this. All right, so what am I doing here? I'm sticking two benzene rings to each other, right? Sticking two benzene rings to each other, meaning that one of them has to have the diazonium salt on it. Oh, yeah, that's this one. And then what does the other one have to have on it? What does the other benzene ring have to have on it? It has to have an activating group, right? So, of these two groups, which one is my activating group? Right or left? Which is left, right? No. Which is left, right? Right or left? Left. Left is the activating group. Okay. So that solves the problem. But I can present and say, okay, here are my two benzene rings. Here's my activating group. Here's my diazonium salt, and this is my other group. Or I could say, well, what if I actually have my diazonium salt on the same benzene as the benzene with my activating group, right? What if I'm doing this? Either one should work, right? Wrong. Wrong. Maybe I'll do this in lecture, but I'm going to try to explain it. So, remember that this group is the group that is doing the adding, meaning that the other benzene is the benzene that is being added to. If we look at our other benzenes, if we look at this benzene here and this benzene here, if we look at our other benzenes, the groups on those benzenes are going to dictate where this benzene is going to attach. This one on the left-hand side, this benzene is saying, okay, I have an activating group, so I'm going to attach ortho or para. I'm going to make things attach to me ortho or para, meaning that I'm going to make things attach to me probably here because the other group is big and bulky. On the right-hand side, the benzene that is being attached to, or the benzene that is being attacked, has a meta-directing group, right? SO3H is a meta-directing group, so it's going to say that, okay, I want things to attach here. I'm directing them to the meta position, meta to me. So, if I were to do the synthesis with either one of these two reactions, or I mean either one of these two styles of the compounds, what you will see is that on the left-hand side, since I am attaching meta, I will get the desired product, versus on the right-hand side, actually, I think this is a correction to the statement I made earlier. I said that deactivating groups couldn't do this reaction. They can. I apologize. Which brings up the question of how. I'm not sure.
So the delta negative.
What was that?
So the delta negative.
It does. It does. It'd be very weak though, because of the resonance. That carbon is, due to resonance, could be positively charged. So it would have to be on the resonance forms where it does have the delta negative, which are not too common. So that reaction is probably very unfavorable thermodynamically anyway. So point being, we need to pay attention to where the other groups are and what dictates where. If we need to perform a synthesis like this on an exam, we need to be careful to say, okay, I know that I want my benzene with the activating group. I know that I want my benzene with the activating group to attach para. Or if I were to tell you to make this on an exam, okay, I know that I want it to attach meta, not necessarily para. So we need to be mindful of which groups we are adding and which groups we are adding to. Just keep this stuff in mind. It's okay with that room? Yeah.
Is there a base, like water?
there's water in every reaction. Almost every reaction. I'm sure there's a base. I'm actually not certain of the mechanism behind this one. This one's actually really iffy to me right now. I don't like it at all, actually, because it just doesn't make sense.
Do we need a state water?
What was that?
Do we need a state water?
Oh, no. Well, for these reactions, we don't need to say anything. So the idea here is that if we look back at our chart, is it okay if I show the chart? If you look back at our chart, the things that we are adding, a lot of the things that we are adding are either negatively charged or have some nucleophilic property to them. So in terms of having a base, in order to possibly deprotonate and then kick the N2 off or attach somewhere, for these reactions it's not necessary because the things that we are attaching to them have nucleophilic properties to them anyway. I will look over that other mechanism, that one on the right, because it's actually really bothering me. But in terms of stating water or not, the only one that you really need to state water for is this one, because we need to use hydronium ions in order to make the OH group on it. Know this chart. Go on a break. Yep. Can I pause this thing? What was that?
The resonance structure, like when you add that position,
Yeah.
whether or not you could resonate the SO3 and the N2.
Mhm.
Yeah, if you can't resonate, it just resonate the resonance.
What destroys the resonance? Are you talking about the second reaction right here?
The one in meta position.
Yeah. Well, the idea here is that so when we're performing the resonance here, this will end up becoming a carbocation when we have a meta position or a meta directing group. All right. And if that's the case, and this is positively charged, what I'm having trouble with is understanding why a positive charge would attach to a place where there's no positive charge. That's what I'm having trouble understanding. Right? And he was saying earlier, well, it does still have a delta negative whenever the positive charge, so it can't be on both sides at the same time. It'll be here and then it won't be there. And while that's true, that's just a really unfavorable reaction. It just doesn't happen. Like,
And too strong enough? Could that be the reason why?
it could be. I don't know much about the strength of this. That might be the case. I wouldn't focus so much on this as in terms of the meta position addition. If you're going to get this in a question, it'll almost 100% be this. 100% be. We're making a straight
But
change.
anyway.
Because this is how we make methyl.
You're supposed to reflux for an hour and a half.
Yeah, that's from the lab,
She
right?
did 15 minutes. I actually did.
Okay.
Here. When did she come in?
There's H2O in there.
When did she come in?
So-
I don't know. Cool. Down at the same time.
But this reaction is this one.
Yeah.
Yeah. So
10?
yeah, that's how you would make that.
6:10.
The question here would be,
Oh, they said she came
what
in.
happens if I do this with that? Do I even get a reaction? Do I even get a reaction? Honestly, I'm not sure. I thought we would, because this is what it was written in my notes, but these notes were from an external source. It wasn't from the series class. It was from like a review session. And who knows if the person who was providing that information knew it. At myself.
Are we throwing an elimination?
What was that?
To bring aromaticity back to the ring with water.
Yes, yeah. So for all of these reactions, the benzene addition reaction. So not these ones, but these ones. All of them have that feature in them, where we're losing aromaticity and then getting it right back. We talked about that in 118B, where aromatics are very stable. That's why, or they're very stable, meaning they're very unreactive.
Chlorine's acting as a base. To
Well,
reinstate aromaticity for your cross.
in this reaction, yeah, probably. In this reaction, probably. But for all of these, we have the loss of aromaticity, and then we gain it right back because that's a really unfavorable position to be in. The loss of aromaticity. Yeah. Did you have a question?
Yeah.
Go ahead. You can take it.
Last time is like
Yeah.
the last note. Could I take a picture of like I left off
Yeah,
like
yeah.
nitration?
Yes, yes. I need to find it. Here we go. Why am I a lost child? I want to give you the ones that we took in class, not my own personal notes, because I feel like the ones we took in class. They are on the drive. Oh, they're right here. Okay, so you left over here, so it would be this page in the back. Page. Thank you. Thank you. No problem. Yeah, we don't lose. Let's see. Let's see.
Come back to it.
Probably.
But I don't know. I don't usually try to remember stuff. At some point, I try to watch my stuff.
Yeah, I was about to look it up.
just comes to
Huh?
water toast in this.
No.
It would make sense. It would make sense. In my notes, it's not written water. I don't see how it would be implied, but again, there's water in like every aqueous solution. Any solution, if you take benzene in a water, in a beaker, and you pop off the lid of the aroma flask or whatever the beaker, it smells good and it's liquid. It's water. It physically has to be water there in order to mix it up and to have some molarity of any concentration of anything. No, none of these have mechanisms to them. It's just
You're gonna have to look at the periodic.
read and react, so to speak. Like, okay, so I give you a synthesis problem. What do you do? Oh, okay, so let me go through the toolbox of benzene reactions that I have and make something out.
We had to write it for
Which one's activating? Which one's
You have to write the mechanism for the lab?
okay, so, and then
You have to understand that those.
That will probably give you the answer. Yeah, they're not super like strict, I believe, about the mechanisms in the lab. Like if you were to show, because if you Google a mechanism, like it's like a really generic, it's like a really generic mechanism, but like it all works. All these mechanisms work. Like there's nothing about the series mechanisms that are like the gold standard. It happens this way, right? Like any other professor can say that my mechanism is the gold standard happens that way, and their mechanisms could be different than Dr. Series. So just Google it and you'll be fine. No problem.
Dude, I know it's that. I think we're seeing you like,
But if you do remember, it helps you take that. But if you don't remember it, you're gonna have to use the periodic table to actually logically depend on NO2 versus NH2. Those two are like the opposite ends. Like 2's an N. You just have to know which one's the H and O.
Caesar salad. Well, that
The
goes
first
on
page in the back
pizza.
side.
Are you sure that's?
That's why
No,
you put
I
NH2
said-
and NO2. It's to trick you.
And then she said he had salad, and I said,
But
it goes with pizza. But people eat salad with pizza.
Does anyone have pizza for me to eat? I'll eat it.
No, but she said she smelled pizza, but I went for salad.
Right? Completely wrong. Yeah, that's what they're using. NH2 and NR2 are pretty much similar in terms of yeah, that's NR2. Yeah. They're both orthostrips.
activating in the
Yeah. But yeah, that's the thing. Like NO2 and NH2. Yeah, that's okay. Yeah. Is this like yeah.
So it's gonna be
Yeah. That's what it means. But you're gonna put that on the test. I guarantee you, you're gonna put NO2 and NH2 on the test.
What does it do ortho? What does it do ortho?
Because if it's a huge molecule, right? It would like this.
This is considered used without
Yeah. If it was smaller, it would do ortho first before para. It always does ortho first before para. Unless you have a blocking group. Like unless the ortho position is blocked. But this is para position, right?
yeah, therapist, sorry. And then
No, it'll always do para position first before ortho. Typically. I could be wrong. Maybe there's like an N. Like a purity might be a section. Not I think for most attacking, it'll hit para first, and then it'll hit ortho. It won't do ortho first before para. It'll do para first before ortho. That's why if you only want the ortho, right, you need a blocking group. That's from when it can be. I don't remember what the blocking group is. Because you have to have a blocking group. Yeah, it's like that block with the para position. It's like a temporary blocking group. Maybe that disulfide bridge, right? Yeah, I think that would be really helpful. Is that sulfide bridge? I think it's great enough.
That's to protect carbonyls.
Oh, I was thinking of having like a blocking group. Because you know how like
A blocking group for an orthopara?
Yeah, you know how you have your BR2 and the BR3?
You can technically use this. Well, okay, if you want a blocking group for orthopara, you would need. You can use the sulfonation. That blocks para.
Okay, alright.
Yeah, sulfonation blocks para. You could possibly use this reaction to block meta. You could maybe find a way to do it.
Alright, no, because my only concern is that the BR2 will be attached to the too. So I guess it's the sulfonation problem.
Oh.
Because you know how like they get two BR2s and BR3, right? Because what happens here is it attacks here and then here, but my concern is that it'll also attack here as well.
Not if I only have two equivalents.
Only two equivalents? Okay.
Yeah, well, it says two equivalents right
Okay,
there.
alright.
Yeah, so
Okay.
you won't get the third bromination there.
Oh, okay. Alright.
Yeah. Okay. Wait, one more bite. Okay. So that's it for diazonium salt stuff. I'm still chewing. All right. So that's it for diazonium salt stuff. That's it for chapter 21, chapter of amines. This stuff was actually part of chapter 22. But now we're going to move on to the beginning of chapter 22 and talk about more benzene reactions. What am I doing here? All right, so questions. I Googled for like an extensive 30 seconds and I couldn't find any coupling reactions that had deactivating groups on them. The deactivating groups as the group that is being added to. So I don't know if that's a thing. What I will say is, for this reaction, the main point of emphasis is to recognize this. To recognize that if I want to create a straight chain of benzenes, I need an activating group here. That's the main point of emphasis. I actually don't know if this is even a thing. It was written in my notes, but those notes I took from like another source, which I don't know how credible that source may or may not be. They have never misinformed me, but I don't know if this is a mistake or not. But the point is to know that if I want to make a straight chain of benzenes, I need an activating group, and I need to have my activating group on the benzene that doesn't have the diazonium salt on it. I need to have them on separate benzenes so that I can attack like that. Is that cool? All right. Okay, so let's resume by moving on to chapter 22. Was it which is another chapter dedicated to benzenes and semi-specifically benzylic carbons. So benzylic carbons, what does the word benzylic mean? Benzylic is a ship name for benzene and allylic. So you take the word benzene, you take the word allylic, and you make a carbon that is allylic to the benzene. It is one carbon away from the benzene. It is the benzylic carbon. Earlier, someone had brought up the benzylic nitrogen, which means the nitrogen that is allylic to the benzene, essentially. So, we're going to be talking about benzylic carbons and their chemistry and all that good stuff. So, benzylic carbons share a lot of the same reactions, a lot of the same properties as allylic carbons do. If we remember back to chapter 14, we talked about allylic carbons, and we said that allylic carbons were they had very stable conjugates. Stable, just like allylics, meaning that they can support things like carbocations, things like radicals just fine. They can host them just fine. Normally we'd say a radical is very reactive. Normally we'd say a carbocation is pretty reactive. We want to do our best to get out of that situation. But just like allylics, benzylics can handle the heat. I think that's all in terms of properties. You just need to know that. Oh, and they're also, just like allylic carbons, they're more acidic than, say, this carbon, the one that's right next to it. They're more acidic. Do I have that somewhere? I might. Don't remember. Anyway. So we have a few reactions with them. Here I have down 4 that were written. All of the allylic reactions work with this. So things like NBS and things like the substitution reactions that we did previously, those all work. And we're going to go over that. So I remember saying, I might have said before that the reactions of 118B you need to know. I don't know if I've said that before. So that's a recurrent theme in this class. Until after midterm 2. Until halfway after midterm 2. Then it becomes somewhat new chemistry. Because then we're going to be talking about biomolecules. Substitution reactions. So, if y'all remember this classic example where I have this, I have some poor nucleophile, and then I get no reaction because the H2O is a poor nucleophile, so it's not going to perform substitution. Well, just like allylics, benzylics are good for substitution reactions. Substitution, SN here means substitution reactions. SN as in SN1, SN2. So that means that if I have the same compound but just turned the cyclohexane into a, what did I do? Well, the top one wasn't supposed to be a benzene. That was the point. Yep, that's okay. So So let's review that then. So the idea here was to say that normally chlorine's a good leaving group, and I can do a substitution reaction with it. However, because this water is, well, first of all, the chlorine is primary, comes on a primary carbon. Second of all, the H2O is a poor nucleophile. So I have those two things. Those two things are not good for substitution. Substitution reaction doesn't occur. I get no reaction. However, if I have a benzene instead of a cyclohexane, if I have a benzylic carbon now, I can get that substitution reaction. This works via an SN1 mechanism to give me substitution. Oops. This works to give me substitution because it's okay with holding a carbocation. Benzylic carbons are okay with holding a carbocation. So they work just fine. They wait for the slow, poor, bad nucleophile to do its thing via SN1, very slow mechanism. Another example of a different yet still poor nucleophile is an alcohol. Here I have a methanol. With a methanol, I can do a substitution reaction to give myself an ether. Here I can get an ether. This is supposed to be benzylic. And here's a new reaction we're about to discuss. I have a way of removing this guy. I can clip him off. So if I ever need to get rid of a chlorine or get rid of a leaving group that is benzylic, I can do it by this reaction here, by first transforming it into an ether, and by then turning it into a methyl group. Now, this will always give me a methyl group because this reaction can only occur, or it can only remove benzylic ethers. This ether is benzylic. It is one carbon away from the benzene. I'm removing this group here and adding hydrogens to it. CH3, and then I get my alcohol back. Remember that, yes?
Isn't hydrogen with palladium over carbon also add hydrogen to cis alkene?
The benzene is, it's not reactive enough to, you're saying to turn this back into like a cyclohexane?
No, not to the benzene, just if there was a substituent
Oh.
with an alkene on
Oh,
it.
yeah. Mhm. Yes, it'll do that. Yeah, this can, cis and trans, to both cis and trans. It can turn both cis and trans back into, we're adding hydrogens.
Oh, right.
Yeah, what you're thinking of is for alkynes. I can turn an alkyne into either a cis alkene or a trans alkene. Those are specific different reactions. We don't need to worry about those in this class. That was for 118B. That was the Lindlar's catalyst or the LiNH3 reaction for turning alkynes into, oh, I'm surprised I remember that. Alkynes into alkenes. Right. So, this stuff we kind of already knew. This is the new stuff here, is saying, okay, if I want to make a benzylic methyl group, this is how I do it. Convert the leaving group into a benzylic ester, and then pop it off. We're cool with that. All right. So that's one style of reaction I can do. I can do a substitution reaction. I can use benzylic carbons as protecting groups. So, say I want to perform this synthesis. Say I want to perform this synthesis. Okay, so what am I doing here? Okay, I need to add a bunch of carbons to probably, okay, let's see, we have 1, 2, so 2, 1, 2. Okay, I probably need to add a bunch of carbons over here. What if I turn this into a Grignard's reagent? Does that work or not? If it does work, why does it work? And if it doesn't work, why does it not work? We can't do Grignards with alcohols. So, if I want to perform this synthesis, we can't do Grignards. Can't. That's out of the question. Can't perform it with an alcohol because if I were to take the above compound and Grignard dyes it, essentially, this is essentially what you get. This is essentially what you get. You get a negatively charged carbon over here, and this negatively charged carbon is what does the attacking normally in Grignard's reactions. However, here I have a proton on my OH. What it will end up doing is deprotonating the OH, and then I get nowhere. That's not what I wanted. That doesn't do anything for me. I just end up, the best thing I can do here is probably make an ether out of this or turn it back into an alcohol. I don't want either of that. I want to make it into this specific alcohol. I don't want to make an ether as well. So, what do I need to do? I need to protect the alcohol. And I can protect the alcohol benzylic halobenzene, I'm going to call it. We can use this compound here that has the allylic halogen, the benzylic halogen, as a protecting group. And we're going to show how. Jam in on the bottom of this page. So again, remember, the first step that I need to do is to protect the alcohol. That's my concern here. My concern here was earlier I couldn't perform the reaction because my alcohol wasn't protected. But I can protect it with take a look at that. I have an alcohol, like I have an alcohol. I have an alcohol on the bottom, I have an alcohol on the top. I have a leaving group. I am essentially just making an ether. This is essentially just making an ether. This is an ether. And I don't have a problem doing Grignard's reagent. I don't have a problem using a Grignard's reagent, doing the Grignard's reaction with an ether. I have the problem with the alcohol. So now that this is an ether, I have protected my alcohol, and I can perform Grignard's. So, Mg. Right, so I can now use this as a Grignard's reagent, and I can stick it to, what can I stick it to? So let's take a look here. What did I need earlier? I said I had 2 carbons over here. And so I'm going to need how many more carbons? I'm going to need 1, 2, 3, 4 more carbons. I need to add 4 more carbons, and then on this carbon over here, there's an alcohol. So what does that look like? This looks like right? Everyone see that? Because it's this carbon. This carbon. This carbon's doing the attacking. So this carbon is going to stick over here. This will turn into an alcohol with the protonation. And so I have my methyl group sticking off my alcohol, and then I have my 1, 2, 3 carbons. Classic Greenwich reaction question, yes.
You just call that butane?
Yeah. Yes. Butanone. 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 All right, okay. So I did this, and I got, what did I get? Okay. What do I do now? I have one arrow, so that means there's one step left. What can I do? What can I do? What would the acid workup accomplish? Acid workup to clean things up? Good guess. Well, what were you going to say?
It's like concentrated acid.
I can remove the ether, the benzylic ether. It's a benzylic ether. I can remove it just by using hydrogen and the platinum catalyst. And there we go. I kick this thing off. I regenerate my methylbenzene. And then I can probably use that for more synthesis if I need to. But what's important is I got this thing now. Everyone see this? All right. Cool. We did also learn another way to protect alcohols in 118B using, was it acetone? Yeah, probably acetone. Yeah. This is just another way of protecting stuff. I saw someone raise their hand in the back. I'm not sure. Okay. So are we cool with this? It's okay with everyone? So, first reaction we talked about was substitution reactions. The second reaction we talked about was using a benzylic carbon that had a chlorine on it as a protecting group. Another reaction the benzylic carbon. And so we said that benzylics are really similar to allylics. They share a lot of the same reactions. One of these reactions being the NBS or the NCS. So here I'm talking specifically about bromination. But you can also chlorinate using the NBS or the NCS to brominate or chlorinate. So this is my allylic carbon, my benzylic carbon. And we know from 118b, chapter 14, that NBS or NCS will brominate or chlorinate the allylic, in this case, the benzylic carbon. Nice. So now I can use this as a protecting group. I just made a protecting group. We've seen this reaction before. It's just allylic. Let's write that down. This brominates allylic carbon. Brominates allylic carbon and benzylic, because benzylics are allylics. I have other ways to brominate as well. I can use HBr. Yeah. So, that's a mistake. So, on the right side of each reaction is the product, but it's incomplete. I'm missing the bromine. Obviously, I'm brominating. I'm missing the bromine. I didn't write this either. So, let's talk about. Let's start with the left. Start with the left. Here I'm brominating. This is an alkene bromination, but the alkene is also part of the alkene is also part of a benzylic compound. It's a benzylic alkene, essentially, right? So, the bromine group, where does it attach? So what I'm getting here is I'm splitting the double bond. One of them is going to get a hydrogen and one of them is going to get a bromine. Which one gets the bromine? The leftmost carbon or the rightmost carbon? The left. Why would the left get it? More stable. Markovnikov, sure, but they kind of both have the same, they're substituted the same. What it is you get the more stable carbocation. In this position, we end up getting a carbocation. This mechanism requires you to generate a carbocation, and the carbocation is more stable in this spot rather than that spot because it's closer to the benzene, or more specifically, it is the benzylic carbon. Let's show that on the mechanism. So double bonds are an electron source. We know that double bonds are an electron source, meaning that they are going to deprotonate this bromine. They're going to take the proton off. And one of the carbons is going to get the proton and the other one of the carbons is going to get a carbocation. It's going to get a positive charge. And we said we would prefer for the proton to add here and the carbocation to be here because this carbocation is in the benzylic position. It is more stable. It is more favorable than if this were flipped. It is more favorable. And then all we get here is addition, a nucleophilic attack of my bromine, and I get this compound. Somewhat analogous to the Markovnikov reaction. But the idea behind the Markovnikov reaction was to talk about which one is more or less substituted. Here, they're both carbons, both vinyl carbons are substituted the same. So Markovnikov wouldn't be the correct term for it. Now, if we look at the right.
Right?
Yeah, right. So what is this? Where does the BR go? Does it go here or here? It probably goes on the right because I just showed it. The other reaction goes on the left. But why? The peroxide. What does the peroxide do? What do we generate with the peroxide? It's not a carbocation. I couldn't hear what you said. What was it? We form a radical. The peroxide, the whole point of using a peroxide is to form a radical. And when we form the radical prefers to sit in the benzylic spot. The radical electron prefers to sit in the benzylic spot. Let's show that. So the first step is peroxide bonds are very weak. Oxygen-oxygen bonds, oxygen bond with oxygen, those are very weak bonds, so they will split with a little bit of energy from light. They will split, and you will get this compound here. And this compound can react with the hydrogen bromide, with the HBr, to give me, this is beginning of 118B. A bromine free radical. To give me a bromine free radical. We formed an alcohol and we got a bromine free radical. So, I have my double bonds on my benzene. I have my double bond on my allylic carbon, and I have bromine free radical. They will react with each other. Fishhook arrows means one electron is moving. So what we're doing here is we're sticking the benzene onto one of the vinyl carbons and we're moving the free radical electron onto the other carbon. And we said the free radical electron prefers to sit here because that is the allylic spot. That is the benzylic spot. That is the more favorable spot for it, the more stable spot for it. So the bromine will attach to the other carbon. And then all we need to do is reprotonate. And get this compound, our product. And then more free radical bromines to go do whatever the heck it wants to do. Does this make sense, everyone? This is a demonstration. So this is bromination, or, specifically bromination, of the benzylic carbons, demonstrating the stability of carbocations and free radicals in that spot. We have one more reaction. And then we're going to do some very brief introduction of phenols, like super brief. It'll take like 3 minutes. And then we're out of here. So, questions about this? All right.
We have a question.
Yes.
Did the ROH just floats around on the solution, or?
This?
Yeah, the ROH.
Probably.
Okay.
I can see that it would also. I don't know if this is a reversible reaction. I don't think it is. So I'm going to assume that that's its final fate. Yeah, that's probably its fate. Just floats around as alcohol. So, oxidation. The oxidation reaction we can do to the benzylic carbons. We've seen them all before. We've seen all these reactions before, so we're just going to get through them real quick. Oxidation. So the first reaction is using KMNO4. And what does this reaction do?
Turns benzylic carbons into carboxylic acids.
turns the benzylic carbons into carboxylic acids. Very good. Assuming that the benzylic carbon has at least one hydrogen. So, we oxidize to a carboxylic acid here. We have to have at least one hydrogen in this case. We've seen this reaction before. This one is somewhat new. React the benzene with an allylic carbon, with a benzylic carbon with Jones reagent, you get an aldehyde or a ketone. You get an aldehyde with a ketone. Normally we'd be using Jones reagents on alcohols, but this kind of reaction, a Jones reagent on a benzylic carbon, will oxidize a benzylic carbon to an aldehyde ketone. And then lastly, if I use MnO2, what does that do? We've seen this one before. So it oxidizes something, right? But this is an oxidation reaction. That's what the title says, right? What does it oxidize? In this case, we oxidize only benzylic OHs. So here we oxidize only benzylic, but also allylic OHs. So those other OHs, this one and this one, aren't benzylic. They aren't allylic. They are too many carbons away. They don't get oxidized. Only the carbon that has the OH that is benzylic, allylic, one carbon away from the benzene, the next door neighbor, only that one gets oxidized here. So today we covered all of the reactions of diazonium salts. We covered all the reactions of benzylic carbons. We just covered 2 classes of molecules in one day. And at least to me, it didn't feel that bad. So we got like 7 minutes left. I'm going to super briefly go over. We're going to dip our toes into phenols, so that way we can finish all of midterm 2 material on Wednesday, which is all reactions of phenols, and that should be it for midterm 2. So midterm 1 material was nitriles, amines, diazonium salts, benzylic carbons, phenols, or benzylic alcohols. That's it. So, does anyone have any questions about this? All right. Let's do this super fast, because it is super fast. So, phenols. This is a phenol, benzylic alcohol. We're going to start with the nomenclature of it. And the nomenclature of it is simply phenol or phenol or however you want to pronounce it. That's like literally it. So I'm only going to give one example because we only need one example to get the idea down. If I have this compound, I look around and I look for my priority. I see my OH has the highest priority, so this is obviously going to be a phenol of some kind. And so I'm going to go around numbering my carbons. So this is carbon number 1. That would make this carbon number 2, carbon number 3, carbon number 4. Going in order to give the molecule the lowest total number. And then that's it. I just name it 4-bromo. That, yeah, 4-bromo, 2-ethyl, phenol. That's it. Nomenclature done. It's that simple. Questions about this? I didn't assume there would be questions about this. So, like, this is literally the easiest nomenclature. Just, it's phenol. It's nice. I hope you guys get this on your midterm. That's like a free 10 points. So, properties. The main property we're going to talk about as for phenols is their acidity. We refer to amines as like a general base. In this scenario, we're going to be referring to these things as acids because in most of their reactions, they function as acids in the beginning of that mechanism. So, the acidity. And I want to compare the acidity of a phenol versus a cyclohexanol. And I'm going to ask which one is more acidic, the phenol or the cyclohexanol. Is that this way? So we had one vote for phenol. Who votes cyclohexanol? Who votes, okay, phenol. Okay. There's only one person who voted cyclohexanol. Why'd you say that? Just curiosity.
I was just thinking benzene was going to pull down against the OH, or I don't know.
You said for this one, right? Yeah. That's exactly what it is. So, remember, when we're talking about acidity of compounds attached to the benzenes, we're referring to here specifically this hydrogen. So let me draw it this way. That hydrogen. This hydrogen is going to be less electron dense than this hydrogen because here I have electrons. This isn't proper, but I'm drawing it like this anyway. Electrons flowing from the aliphatic chain through into the alcohol over to the hydrogen. Because this OH here acts as an electron puller, electron withdrawer. So that OH is more electron rich. And remember, we want acids to be electron poor. So those bonds can be weaker. And this is more electron rich, which means that it's less acidic. Whereas over here on the right, remember this is a benzene activator. OH is an activating group, meaning that the OH will supply electrons to the benzene ring. It pushes electrons into the benzene ring. And if the oxygen is pushing electrons into the benzene ring, it's moving electrons from here down into here. This OH is losing its electron buddies, neighbors, over. So that means that this H right here is electron deficient because the OH supplies electrons to the ring. Means that it's less electron rich, which means less acidic. So this is more acidic. Done. Okay, if y'all have any questions, come ask me. Wednesday, we will finish midterm 2 material. Fun.